welcome you to my lecture today. Of course, today I'm going to be walking you through what we call two-sample randomization test. Before now, I think I published a different topic for today before, which I call simulations on randomization, but I canceled that. I canceled that based on based on feedbacks that I got from students. I want to appreciate those who visited my office hour yesterday. And of course, I told you, giving feedbacks is very, very helpful a lot. So because of that, because of the feedback that I got, I think I need to make some clarification about the quick, what the previous topic that we did, particularly when we're talking about parametric tests. You're given set of data and you have to decide on which test is appropriate. So that is the reason why in today's lecture, if you look at the outline, I'm going to spend some time on quick reviews before I go into today's topic. Now, this is the situation. I'm going to start with a quick review now. And I need you to listen. There have been kind of controversy around the use of t-tests and z-tests. Please, I need you to pay attention, okay? There have been controversy around which one is appropriate between the z-test and a t-test. Then I actually want to, make a clarification on that today. Now, this is it. When you check online, I told you the other time, even though at times we get useful information online, but the facts also remain that you can also get some misinformation too. Okay. And that is why you basically need to search from several sources. Like when you are learning, you need to be able to, apart from the fact that you basically going to rely on whatever we tell you, you also need to consult other sources as well. Now, this is the situation. When you check online, they're going to tell you, okay, when the sample size is large, use z-test. When the sample size is small, use t-test. No way. I want to tell you now, this is the situation. You got a population you're choosing from, right? And you also you're choosing sample, right? Now, when the population is normal, I'm going to say this again. When the population you're choosing from is normal, irrespective of the sample size that you are choosing, provided the population standard deviation is given, then you're going to use z-test. I'm going to say that again. When the population you are choosing from is normal, irrespective of the sample size. Look at the word irrespective. Whether the sample size is large or small, provided that the population standard deviation is known, you're going to use z-test. That is a condition number one for you to use a z-test. What is the condition number two to use a z-test? The population the population you are choosing from is not normal, right? I'm going to say that again. The population standard deviation you're choosing from, the population you are choosing from is non-normal, but the sample size is large. When I say sample size is large, at least story. Okay? When I say sample size is large, at least story, provided the population standard deviation is known, you're going to use z-test. Now, if you look at what I just said now, what actually determine the use of z-test is basically the population standard deviation when it is known. Look at that. When the population standard deviation is known, it's very, very crucial to the use of z-test. I'm going to say that again before I go into that of t-test. For z-test, for you to use z-test, when the population is normal, irrespective of the sample size, provided that the population standard deviation is known, you're basically going to use z-test. Another condition for using z-test, when the population is not normal, like the population distribution is not normal, but the sample size is large. And how large is the sample size? It has to be at least story, provided the population standard deviation is known, you're going to use z-test. Now, let me now tell you when we need to use t-test. We need to use t-test. I'm going to give you the condition number 1. When the population you are choosing from is normal, okay? The population you are choosing from is normal, irrespective of the sample size. Irrespective of the sample size, provided the population standard deviation is unknown. Look at that. Population standard deviation unknown, you use t-test. Excuse me. Does that make sense? T-test. Now, when you now take a look at the t-test, let me tell you the first 2 conditions. Of course, whether t-test or z-test, whether t-test or z-test, is either your population is normal or you're taking a large sample size. You get what I mean? But what distinguishes them is whether population standard deviation is known or the population standard deviation is unknown. But let me tell you the situation. When the population is normal, the sample size is large. Population is normal, sample size is large, okay? But the population standard deviation is unknown. It's still going to be a t-test. Even though population is normal, sample size is large, but you're still going to use t-test. Why? Because the population standard deviation is unknown. What is the determinant now? The determinant is whether the population standard deviation is known or unknown. What of in this situation? The population is not normal. The sample size is small. Oh my God, parametric procedure fails. When I say parametric procedure, whether T or Z, the 2 of them will fail. Let me tell you the condition under which they're going to fail. The 2 of them will fail. Population is not normal. Sample size is not large. Then what is the alternative? I mean, what is the alternative procedure? The alternative procedure is either to go with bootstrapping or to consider non-parametric tests. Because that's a double tragedy. Population is not normal. The sample size is small. Look at that. That's a double tragedy. Any question? Have I been able to clarify that? Any question? Any question? Okay, go ahead. Oh, okay. The Z for proportion, we always use z-test, but there's an assumption underlying the use of z-test for proportion, provided the products of N and P. Sometimes we will say greater or equal to 10. Some will say greater or equal to 15. Let me just say at least greater or equal to 10. But it's always going to be z-test. There is no any condition where we're going to use t-test for proportion. No condition. We're always going to use z-test. If the condition of z-test fails, then it's basically going to be something else. But it's not going to be a t-test. That's a good question. Any other question? Okay. Let's go into the slide. We can also bootstrap standard deviation. I'm going to say that again. The same way that we bootstrap mean, we can also bootstrap standard deviation. Now, the code on the board is to bootstrap standard deviation. The MED that you see, that is the data. The MED is the data, right? So this is a code now. If you're giving some observation now and they want you to bootstrap standard deviation, you can bootstrap that. The same way mean can be bootstrapped, standard deviation can also be bootstrapped. Okay, that is the code I'm just trying to show you on the board. Okay, and of course, I've told you, you can use, when you're talking about, in bootstrapping, we're talking about confidence interval. We have a bootstrap T confidence interval. We have a percentile. Okay, and we also have another one, the PCA one. But let me tell you this: when do we use bootstrap T confidence? We use bootstrap T confidence when, after getting your bootstrap statistic and the bootstrap distribution is normal. When the bootstrap distribution is not normal, then using bootstrap T confidence will be inappropriate. How are you going to know whether whether your bootstrap distribution will be normal or not, depending on the histogram? Do you want to ask question? Yeah, you can ask me question instead of asking your colleague when you are in class. So thank you. Okay, now if I bootstrap and the distribution is not normal, I cannot use bootstrap T. But there's a condition to use percentile bootstrap. When the bias is small, we use percentile. But when the bias is not small and the distribution is not normal, the bootstrap distribution is not normal, then we use the other one, the BCA one, because the BCA one corrects for skewness and bias at the same time. It is not as if our modules are failing us, just like what I used to say, but we are the one that we're not doing the right thing. If we're following assumptions, there's not going to be any issue. It's just like living in a state and you don't want to follow the rules and regulation on that state, that person is going to get into trouble. That is the same thing, using inappropriate model for given situation. But let me tell you this: you may use inappropriate model for a given problem, and maybe you get a good result. That very result is what I'm actually going to call an accidental discharge of nature. You got that? Due to accidental discharge of nature. That kind of result will never stand the test of time. Take a look at this. I'm gonna write something funny. You're gonna say something funny now. 64 divided by 16. Somebody online, I'm gonna write for you too. 64 divided by 16. Of course, everybody know the result is 4, right? But somebody now decided to do this. The person still get 4, right? But this approach is wrong. Can I go this way? Can I cancel 6 out? No. But accidentally, the result give 4. This result can never stand a test of time, because if they give you a different problem, you are not going to get a result. You're not going to get a good result. Because somebody is going to say, oh, you say my method is inappropriate, but my method is working for me. It's only going to work for you for a while. That result will never stand a test of time. Okay. Having said that, I'm going to go into what I have for you today. So I appreciate those who have been giving feedback. Okay. I spent more time reviewing today because of the feedback that I got. So you're highly appreciated for doing that. Now, okay, I want to continue with the randomization test. But this time around, I want to welcome you to 2 sample randomization tests. But let me tell you this. When you are actually comparing means in 2 populations, you want to compare means in 2 populations, the only condition under which you're actually going to use the parametric method, the conventional parametric method, is when assumption hold. Why do we find ourselves in a situation where we need to perform a randomization test? Because assumption fails. Assumption using the normal theory fails. Oh my God, let me tell you, if I want to compare 2 means, then the probability distribution of the difference of the means must follow normal distribution. The test statistic that I'm actually going to use, whether I'm going to use a z-test for that or a t-test for that, the test statistic, assuming the null hypothesis is true, has to follow normal distribution. But what if in a situation where it does not follow normal distribution, or even the sample size for the 2 groups is even very small, then we cannot use parametric tests. When I say parametric tests, I'm talking about t-tests or z-tests of difference of means. Then what I'm going to be thinking is whether to go with a randomization test or to go with a non-parametric test. Now, I want to do randomization tests now for 2 sample situations. When you take a look at the example that I gave on the board, that was a special, that was what we call directed reading activity. They call that directed reading activity. Okay. Directed reading activity. I'm actually going to write that for the guy online. Directed reading activity. Now, you know what happened? The data set that you're actually seeing now, okay, they are trying to test the effects of directed reading activity on, the degree of reading power of elementary school students. Okay, the elementary school student, I think in this example, they were focusing on the 3rd graders. They basically want to see, okay, using this method, directed reading activity, they basically want to look at the effects on, on what we call degree of reading power degree of reading power that we call DRP. So they are looking at the effects of directed reading activity on the degree of reading power. They basically want to see if we apply our directed reading activity or we don't apply it, does it have any effect on the reading power of a third grader? But you know what? They only have data set on 6 third graders. Oh my God, 6. Now, when they have data on 6 third graders, they partition them into 2 groups. Okay, they're basically going to have control. The control is going to be without directed reading or activity, and treatment group. Okay, the treatment group is the directed reading now. So here in one group, they make use of 2, they make use of 4. We got 6 in general, 6 students in general. Of course, you and I know if we want to compare, which means they need the DPR score. The DPR score here and the DPR score here. You and I know that this is very, very too small for us to use the parametric approach of the difference of means. Now, do you know the data set that I'm actually displaying now? If you take a look at the original sample, let me tell you this, even though they have more than 6 students in that class, but maybe they choose the original sample of 6 students from the entire student, and what I display in number 1 here, in the first group, you can see 24, 61. Okay, the 24, the 61 is actually those the 2 students in one group. The DPR score, after applying this the reading method, and with me, some students were subjected to the new treatment. Some students were not subjected to the new treatment. And what they try to do now, they basically want to compare the DPR score of the 2 groups. But in one group, they make use of 2 students. The original sample that I have here, these are the DPR score of those 2 students. These are the DPR score on the other 4 students in the other group. Therefore, the first one here is basically the original sample. Now, what are we going to do? Find the mean of the first one, of the first group, the mean of the second group, then you subtract. That will give you 3.0. That very 3 is the test statistic when the HO is true. That is the original one. But do you know what we want to do? As we normally, when you want to bootstrap, we basically want to have several versions of the original sample. That is what you see here. But what is going to tell us now? What is going to tell us? How many arrangements are we going to have? Then the idea of the combinatorial analysis will come into play. Oh, I have 6 students, right? And I partition them into 2 groups, okay, in such a way that I want to have 2 here, I want to have 4 here. That would be 6 factorial divided by 2 factorial, 4 factorial. This is going to tell me the numbers of repetitions that I'm actually going to have, number of stuff like this that I'm actually going to have. Now, this is the process. The first step here is the difference between the means and the original sample. Then the second step, the third step. Now you're basically going to see number 4 said I should repeat that at least 5,000 times. Why do I want to do that? In 5,000 times, it may not be all the time that I'm going to use 5,000 times. Let me tell you this. There are some arrangement that may resolve into millions. I'm going to say, okay, let's just use 5,000. And there are some arrangement that may not even get to 5,000, which I'm going to demonstrate today. Okay, I'm going to go now. based on what we're doing now, we are not going to use 5,000. Why? Because the reason why we're not going to use 5,000, the possible number of arrangement that we can have is 15. Look at that, it's 15. Whatever repetition that we want to do will be 15 times. We're not going to go 5,000 times. Any question? How do I get the 15? I got 6 students. Then I want to partition them into 2 groups, 2 in one group, 4 in the other group. I'm actually going to use 6 factorial. Okay, that is what you see now, 6 combination 2. That will be 15 unique arrangements. Oh my God, 15 unique arrangement is what I'm actually going to have. Now, if I want to determine my p-value now, what I'm going to do, if I'm going to have 15 unique arrangements, then I'm basically going to have 15 different differences. Isn't it? This guy that I show here is one of them. This guy. I'm going to have this guy in 15 ways. 15 ways. But you know what I'm interested in? If I want to figure out my p-value, okay, and I want to count the number of these, that is greater than the initial difference that I got. The initial difference that I got is 3, right? Don't forget, some going to be negative, some are going to be positive. I normally like using the absolute value. Does that make sense? I want to count what is the number. They are 15 in number. And that is the reason when you take a look at this. What is it telling you? Oh, out of the 15 arrangement, it is only 12 of the 15 that have their value greater than 3 in absolute term. Any question? Did I use 5,000 here? No, I did not use 5,000 here. The idea of using 5,000 is when the number of unique arrangements that you got using the combination formula is very, very high. Any question? Super easy, right? Okay, now that is why, now we're going to take a look at this now. The p-value is this guy. Just 12 divided by 15. Nothing like 5,000 here. Okay, now, of course, when the p-value is 0.8, that is greater than any reasonable level of significance, you're basically going to fail to reject the non-hypothesis. When you fail to reject the non-hypothesis, you know what you're telling the world, then that directed reading activity does not have any effect. What you're trying to say, there's no significant difference between the reading power of those students who receive directed reading activity program and those who do not. That's what you're trying to say. Any question? Go ahead. Yeah. Oh, of course. There's gonna be a code. That's a good question because it's gonna take forever. Like, yeah. So we have a code in now. That's a very good question. Now you're gonna see the code now, because you know why? I'm gonna show you a code in a situation where the number of arrangement is even more. Let's go. Let's go there. You're gonna see now. Let's take a look at this. This is another question. A sample of 24 adults is randomly divided equally into groups, and a list of 24 what they give them the list of 24 what to memorize. Look at that. 24. I want to partition them into 12 and 12. If you do 24 factorial divided by 12 factorial, this is going to go into billions. Your computer can never handle that. Because what you're going to have, the unique arrangement is going to be so huge. So for the person online, what I'm trying to say here, you basically, the number of unique arrangement is going to be 24 factorial divided by 12 factorial and 12 factorial, because you want to put 12 in each group. Then you're going to have a lot of numbers in millions of billions. But what do we normally do? We approximate that with 5,000 replications. Okay, now, because now here, what they are testing here, they gave some we have a sleep group, and we have those that they give caffeine, and they gave them some words to memorize, and in the end, they basically want to see how many words out of the words that they memorize, how many of that they can they recall. Now, I'm going to show you how you can do that. This is the data set. The data set is only showing you for sleep. We have a lot. When I say head, in R, it's only going to give you the first 6, right? There's so many. Let's take a look at this. Oh, this is a code you were talking about. It's going to look like this. But this very code here, before I first give you the mean, the difference between the mean in the original sample. This is the original sample. What I'm showing now is the original sample. What is the difference of mean in the original sample? This minus that. That is 3, right? How many of this arrangement do we want? 5,000, but initially it's supposed to be billions. If you want to go by the combinatorial analysis, our computer cannot handle that. That's why we settle for 5,000. Okay, now this is another unique arrangement. This is one of the arrangements. In this arrangement now, the difference of mean is 2. How many of that are we going to have? Oh, we want that in a 5,000 way. Oh my God, in a 5,000 way, this is it. Do that 5,000 times. This is the code you are asking for. When you do that 5,000 times now, then you'll be able to compute the difference of means. How many values for the difference of means are you going to have? 5,000 of them. Out of the 5,000, how many of them is greater than the original difference? When I say the original difference, how many of them greater than 3? Before you go into the bootstrapping. Now, this is what we're doing here. And in the end, giving me this as the p-value, the meaning. If I really want to know, if you multiply this guy by 5,000, do that now. That will give you the number that is greater than 3. The number that is greater than 3 if you want to know if this is a p-value. Because to get this p-value, it is a ratio of the number of differences greater than the original difference divided by the totality. So here now, to get this p-value now, you are dividing something by 5,000. Any question? By 5,000 to get that. And what is the conclusion now? 0.0546. That is greater than 0.05 level of significance. And you're going to say there's no difference. There's no significant difference. What am I showing you now? Oh, this is a randomization distribution. Where do I expect the center of the randomization distribution to be? It should be at 0. Why? Because under the null hypothesis, there is no difference between the two means. Because the randomization distribution should centered on the true value of the H0 of the null hypothesis. That is why it has to center on 0. We are talking about differences. Now, we got a remarks. You can actually, I said randomization distribution is created under the null hypothesis being true. By comparison, the bootstrap is centered at the value. Don't forget the bootstrap that we always do, centered on the original value of the statistic. Okay, so the same way that we compute confidence interval in parametric, we also do that in the bootstrapping. Now take a look at this guy. Okay, this guy here, what is he talking about? Oh, this is like centered on 3. Why is it centered on 3? Okay, that was the original 3 that we got, right? And what is the meaning of this? Okay, this is the bootstrap confidence interval. But what about this? This is for the randomization distribution. When you conduct a test, okay, the distribution will be called randomization distribution. When you construct confidence interval, okay, the distribution will be called bootstrap distribution. Oh my God, that is going to be the end. I don't want to stop. Okay. Is there any question before I go today? You know, some of you have been wondering about how the exam is going to look like. And I said this week, before the end of this week, you're basically going to see a practice question for the midterm one. And of course, before the midterm one, I'm actually going to come to this class where I'm going to walk you through those practice questions. I'm also going to tell you what are the areas that will be covered in the midterm one. Not only that, I'm also going to let you know what are the materials that you're actually going to bring into the exam hall. And I want to use this opportunity to appreciate once again those who provided feedback. How am I going to know somebody is sick if the person did not tell me he's sick? I want to hear from you. Somebody who doesn't understand now, but the moment he or she reach out, I want to believe in problem disclosed is problem solved. Problem disclosed is problem solved. Okay, problem disclosed, okay, is problem solved. I understand the fact that some people don't want to, you know, they don't want to tell people about what they are going through. I understand, maybe because they cannot trust the person, but let me tell you, you can trust me. Whatever we discuss will be treated with an absolute degree of confidentiality. It's another weekend. Make sure you stay safe and have a beautiful day. Bye for now, everyone.